Hi everyone, welcome to another video for the AP Physics FRQs, AP Physics 1, and this is the 2026 FRQ number 3. And yeah, so all this text is useless except for down here it tells us how much time it recommends you spend on each question. And for question 3, it recommends we spend 25 minutes. And just so you guys know, FRQ 3 is always a experimental question, so there's going to be like students doing an experiment, and you have to like help them make an equation to find what they're finding, and there's often going to be like limitations, like, oh, they can't measure velocity, they can't measure the mass, or something like that. And lastly, this is version J, it's the only one College Board released. So, and yeah, let's get started. So it tells us that a group of students are investigating friction using the following procedure. The students release a block of unknown mass, so we don't get to know the mass, near the top of a curved ramp, which is shown in the figure here. The block slides down the ramp. The block then transitions to a horizontal surface, as shown in figure 1. Frictional forces are negligible between the block and the curved ramp, but there is friction between the block and the horizontal surface. So you see right here where there's the curve, right here, friction is 0, it's negligible. Right here where they made the lines like jaggedy, that's where we actually have friction. And then the students are asked to perform an experiment in which a single quantity is varied in order to collect data that could be graphed to determine the value of mu k, which is the coefficient of kinetic friction between the block and the horizontal surface. The students have access to only a meter stick. So what does that mean? They only have a meter stick. No, we can't find mass, we can't find velocity, we can't find time. It's going to be very difficult. Not that difficult, but it's going to need us to use a lot of, like, manipulating a lot of equations. So, part A asks us to indicate quantities that could be measured by the students that would allow them to determine mu k using a linear graph. Please, okay. So, we need to find which quantities that could be measured by the students that would allow them to determine mu k using a linear graph. So, how could they, what should they measure and how should they use it? And describe a method to reduce experimental uncertainty for the measured quantities. So, if we want to know what's measured, first we have to make an equation, or else we have no idea what they're going to measure. So we know they have a meter stick, so this is going to need a lot of work just to find a relationship between mu k. So we can do this work off to the side, and just give me a minute to get the equation sheet. Okay, so that got part of the equation sheet here, which should have everything that we're going to need. And I'm just going to try to manipulate them in order to find mu k related to something that we can measure using this graph. So I know the only equation in the equation sheet that has mu k is that the force of friction, so FF, is equal to mu k times force normal. Okay, I know force normal is mg, and then mu k. mg mu k is equal to force of friction. From here, I know that the force of friction is the only force applied on the object after it leaves here. When it's here, there's going to be normal and gravity, but they cancel out, so the only force really is just the force of friction. So I can actually use Newton's second law, where net force, this one, acceleration is equal to net force over m. I'm going to flip, I'm going to F net equals ma. So the force of friction, we said it's the only force applied on the object. We can actually just replace it with ma, which also helps us remove a, because remember it's unknown mass, so we don't know. So that's a good way to start. Mu k mg. From here, I know m's cancel. I am left with a is equal to mu k g. Okay, and again, I can't measure acceleration, so I have to replace it with something else. What can I replace it with? I don't have time, so I know I'm going to have to use this equation, because all the other kinematics have that. So I'm going to try to see how I can relate acceleration. So we have the equation v squared. V squared equals v initial squared plus 2 times a change in x. So what I can do is, I know that the final, if I'm going to consider final is where it stops. So the final velocity is going to be 0. The initial velocity, we don't know it yet, so I'm just going to leave it. But let's just solve for acceleration for now. So I get negative v0 squared over the change in x. The change in x, since we said that v initial v final is 0, I'm going to say that v initial is the velocity as soon as it enters the rigid path, as soon as it enters the horizontal path. So at this point, so that means the change in x is going to be the distance until it stops. So that's going to be our change in x. The distance until the block stops. Yeah, change in x. And then v final is going to be v final is 0 because that's when it stops. V initial is going to be right here. So v initial and then v0. There's more than one way to solve this. This is just the way I did it on the exam, so I'm just going to be showing this way. And then there's also a 2, so we're just going to add this on the bottom. Is equal to a. Okay, so we have this. Let's just plug it in for now. So now we have, let's just move on to off to the side. Negative v0 squared over 2 delta x is equal to mu k g. Oh, and g is negative since we're going to take the downward as negative. So mu k negative g, and then the negatives are going to cancel with this side. So last thing we have a meter stick, so we can measure delta x. Gravity is a constant. Mu k we're solving for. We still don't have velocity. We can't measure velocity. So how can we relate it using this? The best thing would be because we need the velocity right here. The velocity would be the conservation of energy. Since we know from here to here, there's no friction, that means energy is conserved. At the top, it was at rest. It was released from rest. So at the top, the energy is equal to, it's all potential, and potential would be mgh, where h is where it's released. And then right here, at the end, h is going to be 0. It's going to be all kinetic, no more potential. So we're going to have the energy is equal to 1 over 2 mv squared. So let's just set that equal to, and then we can solve for v, and everything would be a constant except for h, which we can measure since we have a ruler. So we come down here for the v. This one we're going to come right here. We have mgh is equal to 1 over 2 mv squared. Masses cancel. We're just going to solve for v. We get 2gh square root equals v. I just multiplied both sides by 2 and took the square root. So I can plug this in again. So we're going to get, square root 2gh, and that's going to be squared. So just 2gh over 2 delta x is equal to mu k g. G's cancel, the 2's cancel. I'm left with h over delta x is equal to mu k. Mu k. And height is, as I labeled it on the diagram, height is this distance, the distance where we drop the block from, which we can vary, or the students could vary. And then the change in x is the distance that it travels on the horizontal surface, and that is something else we can measure with using a ruler. So this is a viable equation for it. So just a quick highlight of what we did. We just started with an equation with mu k, and we just kept working towards removing everything that couldn't be measured with a ruler. So we started, I have to remove mass, we removed it. I have to remove acceleration, we removed it. And we have to remove velocity, and we did that until we're left with mu k equal to only variables or constants that can be measured with a ruler, or a constant like gravity, which cancel in the end. So that's good. So indicate the quantities that could be measured by the students that would allow them to determine mu k. So our answer would be, let's just do it over here. The students, let me type it actually. The students can measure the height. Remember, they don't have h. They didn't give us h. They didn't give us change x. So I can't just say they can measure h. I have to say the height from where the block is dropped from, where the block is dropped from, and the distance it travels. The distance the block travels on the horizontal path, on the horizontal, what do they call it? I just want to make sure that it's a horizontal surface. Like that is the answer for part AI. The students, no, it's students. And then for part 2, it says describe a method to reduce experimental uncertainty. It's the same thing across all questions, AP Physics for this, just they should repeat the measurements from different heights, and from different heights, multiple times to reduce uncertainty. And that's it for this one. And that is it for part A. Part B says, indicate what quantities the students can graph on the horizontal and vertical axis to create a linear graph that can be used to determine mu k. So we found that, let me zoom in, we found that mu k is equal to, I don't remember, h over delta x. H over delta x. H over delta x. That is an h. H over delta x. Okay, and so if we assume that this is the slope, we can do this is the y, this is the x, and so then the slope would be mu k. So we just clearly state, we indicate using text, do not like write something. You just say, by graphing, and remember we can't use h and delta x because that's not given unless you like, I guess you could off the side just label them, but it's just safe to do this way. By graphing the height the block is dropped from, oh yeah, I'm not gonna write it all. Just graph height block is dropped from on y-axis. Distance traveled on horizontal on the x-axis. Sorry about that. Like that. Part 2. Briefly describe the relationship between mu k and a feature of the graph from part B. Your answer may include an equation that relates mu k and the chosen feature of your graph. So it can be any feature that we have on the graph. So let's just draw our graph real quick, just to imagine it. Our graph is going to be this, and I have y here and x here. So describe the relationship between mu k and a feature of the graph from part B. So we would answer this by just saying, okay, so I just have to double check because this is very confusing. But basically we already answered this question just like redundant. The relationship between mu k and a feature of the graph, you just literally just put mu k will be the slope of our graph, of the graph. And that's it. It's a very weird question. I don't know why they put it there. But anyways, yeah, that is it for part A and B. And then there's part C and D. For me, experimental is like one of, it's not hard, it's just annoying because it's very long compared to other ones. Anyways, so then in a different experiment, the students release a block from rest on a rough ramp. So the whole ramp is rough, and they release it from rest. The block is released a distance d from a photo gate. So there's a photo gate. The ramp is, I'm pretty sure photo gate measures velocity, but I'm not sure. The ramp is inclined, yeah, I'm pretty sure it does. The ramp is inclined at an angle theta above the horizontal, so they gave us theta. Theta is given, that's good. As shown in figure 2, the block slides down the ramp and passes through the photo gate, which is positioned near the bottom of the ramp. The photo gate determines the speed, yeah. So the photo gate determines the speed v of the block as it passes through the photo gate. The unknown coefficient of kinetic friction between the block and the ramp is mu k. The experiment is repeated several times. This is for the uncertainty, which with different release distances d for the same block. Table 1 shows the measured values of d and v. So you have the distance released from, so which is the hypotenuse distance, or the, I don't know what it's called, angle distance, and then velocity measured by the photo gate. The student correctly determines that the relationship between d and v is given by this big thing, which looks kind of confusing, but if you think about it really, this is a constant, this is a constant, this is mu k multiplied by a constant, and then you have your two things that they gave you, v squared and d. Okay, theta equals 30, they gave us theta. The student wants to determine mu k. The students created a graph of d plotted on the horizontal axis. So they have this, they have d right here. So, what it's asking us, label the vertical axis of figure 3 with a measure of calculated quantity, include units as appropriate, and they should yield a linear graph that can be used to determine mu k. Oops. My bad. Okay, so if we're told we have this equation, they're telling that d is on the horizontal. Just imagine that we have y equals mx plus b. So y equals mx plus b. There's no plus b, so let's just erase that. The slope is going to be this thing. Okay? The x, as they already told us, is d. So then y is going to be v squared. So on the vertical axis, we want to graph v squared. Another way to look at it, if you don't like to look at it, the way I like to do it is like, okay, I have v squared over d. That's horrible. V squared over d is equal to this thing, which means this is the y-axis, this is the x-axis, as they did, horizontal. So yeah, so we're going to be graphing v squared on the y-axis. So let's just come over here. Label the vertical axis of figure 3 with a measured calculated quantity. Let's label it. So I'm going to put, let me just flip this over. I'm going to write, well, we said v squared. V squared, and the unit would be, if it was meters per second, now it's meters squared per second squared. Like that. Then what do they want from us? On the grid provided in figure 3, create a graph can be used to determine mu k. Clearly label the vertical axis with a numerical scale. Plot the corresponding data points on the grid. Okay, we did that. Okay, so we need a numerical scale. So I'm just going to write out the table real quick, and then we can continue from there. Okay, so I'm just lazy. I just used AI to get the v squared values. But anyways, so now we can just graph it. But first we need to label the vertical axis with a numerical scale. So you know, see how this is from 0 to 0.6. We have to do the same thing for v squared. I can see that v squared is like, let's start at 0, of course. And then it goes up to 0.27, so I'm going to round up to 0.3. So I have 1, 2, 3, 4, 5, 6. So I'm just going to make each 2 equal to 0.1. I'm going to have, this is 0.1. This is a bit too close. I'll just do it in a different color. This is, okay, so 1, 2. This is 0.1. This is 0.2. And then this is 0.3. Makes sense? And then, yeah, that's it. And then let's just graph the points. And I'm just going to do it real quick. And that is it. I plot all the points. And remember, it's important that you plot it with an X and not a period, because technically a point shows that it has like an X just shows that it's exactly 1 point, and I don't know, a dot just doesn't. I don't know why. But anyways, also I didn't point that out, but on the test they did give you this right here. It would be a table where you could, if you want, include more data points. Sometimes they require it. For this one, for some reason, they just said it's optional for scratch work and will not be scored. But yeah, so that's what we did. We plotted the corresponding data points on the grid, and we labeled the vertical axis with numbers numerically and with a label. So we finished part C. Part D said, part C3, draw best line of best fit. So let's just draw a line of best fit. Remember, for line of best fit, you just had, it's a good rule of thumb is just have the same amount of points on each side of the line. Like right here, if I do it like this, I have 2 above, 2 under, and like 1 exact. So this is actually a pretty good line. Oops, it moved. But yeah, so I'm going to do 2 above, 2 under, and then 1. If it goes through, that's good. Like that. Okay. Using line of best fit, calculate experimental value. Okay, that's the last thing. Experimental value. So remember, it's the slope. So let's just get 2 points. I'm going to use 0, 0. Let's just find something that's like perfectly, it crosses the line. This one's good enough. This one. Which is 0.44. The point is 0.44. 0.44, comma what? Comma 0.2. Comma 0.2. And then I have 0, comma 0. I'm just going to do 0.2 minus, just slope formula to find the slope. Minus 0.44. Yeah, 0.44 minus 0. I get 0.2 over 0.44. I'll put that into calculator later on. Those are 4s. 0.44. And then, but remember, our slope is not equal to mu k. We are calculating mu k. Our slope is this thing. So I have 2 times 9.8, which is g. 2 times 2 times 9.8, which is, I don't want to do that. I think it's 19.6. Yeah, so 19.6. 19.6 times sine 30. Sine 30 minus mu k, which is what we're solving for. Mu k cosine 30. Cosine 30. And yeah, that's it. And that's equal to, based on our experiment, 0.2 over 0.44. And then I'm just going to like put this in decimals and see what I get. Okay, so I plotted the equation that we got into decimals. But remember, you have to change it to degrees because we're using sine 30, cosine 30. And we get an answer of 0.55. So I have mu k. If you don't understand, for the decimals, I put this equation in, and I set it equal to 0.2 over, let me show you guys, 0.2 over 0.44. And so then x is our mu k. So when x this x is, the decimal just gives us the answer as 0.55. And so based on the decimals, we get mu k is equal to 0.55. And since it's the coefficient of kinetic friction, there's no unit. And yeah, so we're done with it. And that is how you do FRQ number 3. Thank you guys for watching.